So what today is about, it'll start off a little bit like yesterday where there would be a graph. So here's a simpler graph. There's a simpler graph. There's like a crazier graph. So what they're asking us to do is imagine, that's not through my chalk. Imagine that this is getting like turned in 3D to carve out a solid shape. And this is like the pivot point. Like you might have seen people that grill with a thing that like they turn their grill. It's like a rotisserie, I think that's what that's called. Where it like, goes through space. If we took this shape, and this was like our swivel point, and we rotated that in space around the x-axis, what shape would that create for us?
A sphere?
It would create a sphere. Right? Geometry could figure out the volume of the sphere. If we took something like this, and we just swivel that around the x-axis, what shape would that carve out? A cone. We could figure out the volume of a cone using geometry stuff. If I took this and rotated it around the x-axis, you'd get a really pretty crazy looking shape that would probably look like, if it were skinny enough, like a bedpost or a railing or a table leg, or like you have those things that are like all like carved out to be these oddball shapes. But to figure out the volume of one of those oddball shapes, it's like impossible with geometry because they're too unpredictable. But we're carving out a shape like that. Okay, so what we did yesterday was we divided this up into pieces, and we'll still do that today. And we envisioned that each piece was basically it's the closest shape to those. Rectangle was close enough. So today what we're envisioning is if we have a rectangle and we swivel that around in space, what shape would a rectangle swiveled around in space carve out? A cylinder. It would be like these sort of like flat discs sort of stacked together. If you have your book handy, maybe page 274, their pictures are much better than what I can draw on a board. On 274, they did this picture. You imagined a cone. They actually drew a cone. And then they drew these lines where they split that cone up into a lot of discs. Those discs are cylinders. Those are all like short, stubby little cylinders. Then on 275, they took my semicircle picture, and we imagined a sphere, but they actually drew us a sphere. And then they cut it all up into these discs, these cylinders again. I don't think they drew anything that looks like this, but we could use our imagination. You can see the kind of like cylinders that I'm talking about. But that's the concept is we're trying to do a volume. We're trying to do still rectangles are in there, but when rectangles get rotated, they become cylinders, and we're working from cylinders today. Question about the concept? So if anybody's watching this video other than this year, there's a sheet of notes that goes with it. Maybe you want to grab a PDF of that, but that could help you along. So the foundational math formula of this section is that the volume of a cylinder is pi r squared h. So the radius is going to be the height of the rectangle that we have. Like when we swivel this rectangle 3D to make it circular in nature, the radius is the height of the rectangle. Yesterday there were 3 ways we could get heights of rectangles. What was one of the ways that the heights of the rectangles were presented to us or obtained by us?
The book said it.
The book said it. How did they give it to you? In a table. So if they give you a table, that might be a way to go. What's another way we obtain the heights of our rectangles sometimes?
Equation.
There might be an equation. You might have an equation you could plug into, and that's going to be more common today. I don't think we did that at all yesterday in the homework, We did one sample problem where we did an equation, but it didn't, I don't think, appear in the homework. What did you also do in the homework? Number 6, you had to make yourself a graph, and then from a graph, you just sort of look at it and kind of guess like how high it looked. Okay, but in the equation pi r squared h, the r is what we have to obtain. The h is just going to be how wide it is in rectangle form. I know that looks weird because you'd expect the height to run this way. The height runs this way because really the cylinders are like set on their side in a way, like they're all these wheels ready to roll away. They're not like cylinders sitting flat. They're cylinders like stood up on their tip, ready to roll like a wheel. So the h is going to be a choice sort of number. Yesterday we were usually choosing ones as much as we could. If we couldn't do ones, we would do halves or some other sort of convenient number. But here we go. So volume of cylinders is pi r squared h. We're going to have a few cylinders to add per picture. So your first move is going to be to split this up into pieces called intervals. And we're going to want to use the midpoints today. I think we had talked some about that yesterday, that the midpoints were just better. The left sides were okay, the right sides were okay, but the midpoints are better. So we're going to want to figure out how to cut this, figure out where the midpoints are. You're going to want to plug the midpoints into an equation to get the radius. Now I can't rule out that in your entire life the radius might not come from a graph or might not come from a table. But the dominance of tonight's homework is going to be that we're going to plug these midpoints into equations to get the radius. We'd want to square the radius because pi r squared. We'd want to multiply the pi in at some point. We need to multiply the h in at some point. And the h is how wide each piece was going to be. I would suggest it's simpler to multiply the pi and the h last. Like we discovered that yesterday. Just the math was simpler. Instead of multiply, add, it was simpler to add and then multiply once. And that's still the case today. You don't need to multiply at each level by pi, just wait till you're done and get the pi on there, throw the h on there. Then I'm going to work some book examples, and then the homework problems build from the book examples and are greatly similar to that. So example 3 is built off the equation and the picture on page 274. On 274, they give you the simplest equation ever, which is y equals x. Okay, so y equals x is an artificially easy equation to plug into. Most of the homework, you're going to have more work to do than have a y equals x equation, but there is a y equals x problem or two in the homework. On this one, we can see on the picture and from the directions that they're on the x-axis going from 0 to 4. So what would be the most natural amount of pieces to do if you're going from 0 to 4? I'd say 4 pieces, each with a width of 1. If you wanted to make a problem a little easier, it wouldn't be as accurate, but what would be another not bad amount of pieces that would be simpler than 4 pieces? 2 pieces would be simple. What if we wanted to be better than 4 pieces? To keep our math simple, what would be a decent amount of pieces more than 4? Probably 8, because each piece would be half of a space wide. But we're going to go with 4 pieces. So sometimes I'll make a little list for myself, sometimes I don't. Sometimes I make like a little diagram for myself, sometimes I don't. But if we're going from 0 to 4, halfway would be 2, halfway would be 1, halfway again would be 3. We're not plugging those numbers in anywhere. What we want to plug in are the midpoints of those gaps. So this would be half, 1.5, 2.5, 3.5. Up to you whether you like decimals, fractions, mixed numbers, improper fractions, no one cares. What I'm going to suggest, it's going to be handy to usually make a table. Maybe not as necessary on this one, but I think I've found good success with this, so I continue to recommend this. Make a little table where you write down the midpoints. And then we use the midpoints to come up with what the radius would be. Okay, the midpoints are x's. The radius are y's, because they're the heights of things. Given by the equation in this case, y equals x. Usually there's more math to do here, okay, but on this, if y equals x, we're just going to get a duplication of those numbers. But usually y equals some math you have to do to transform those, you understand? Then we're going to want to go not just the radius, but the radius squared, because pi r squared h, we've got to square the radius. So I'm going to go 0.5 squared, 1.5 squared, 2.5 squared, 3.5 squared. And then I cut out of table time. What do we want to do to these? Same thing we did to everything yesterday? Add them all up, and that would add up to 21. And then we're going to multiply by how wide they were, which we can look at this picture if we drew it or imagined it or whatever. How wide was each piece? 1. But we'd also multiply by pi, and this answer will be 21 pi. Something about that? So example 4, I only have partially filled in on this notes paper. So I gave you the equation, y equals the square root of 16 minus x squared. I don't think they make you come up with these equations yourself, okay, but chapter 1, we learned that this was the equation for a circle. If they tell us the radius is 4, 4 squared is 16. If we want to get the y alone, that's where that equation just came from. Okay, y equals the root of 16 minus x squared. If they make you ever come up with an equation like that yourself, it's coming from this. It's coming from chapter 1, review circle stuff. Okay, we can see from the picture, the x-axis is going from -4 to 4, and that's 8 spaces long. How many pieces do you want to cut? I'd want to do 4 also. I'd be willing to do 8, but I don't want to do more than 8. I'd be happier if I only had to do 2, but that seems artificially easy. Okay, so if we think about it, or make a picture if it helps you, if we're going from -4 to 4, little sketch might help you, but what we're chasing are the midpoints. So if we cut up this zone from -4 to 4, what numbers are our midpoint numbers?
3, -1, +1, +3.
Agree. -3, -1, +1, and +3 would be the midpoint numbers. So then let's figure out some radius numbers. The radius numbers are all going to be rooty numbers. It'd be the root of
15.
For which one?
For -1, +1.
For the -1 and +1, we'd get root 15s. How about for the -3, +3? Root 7s. Agreed. Then let's square those radii in this little table thing that I've got set up for you. That's handy because you're just gonna get rid of the roots. So we're looking at regular 3s and regular 15s. Then add them all up. That'll create 44. Sounds right. Yeah. I have a blank sheet in front of me, but yeah, I agree with that. And then times 2 because they're all too wide. Every gap was too wide. If we did this diagram, we'd be going 0 in the middle, -2 there, +2 there. But each thing is spaced by 2's and also multiplied by pi. And that'll total you up to 88 pi. Something about that? Then here's a side trip. Going back to areas. So there's a thing called the average value. If we wanted to figure out what the average value was over time, I'll stand up for a second. If I wanted to know the average value on this shape, I could common sense it because it was steadily rising. And if we just like track like halfway up, like whatever that maxed out at, halfway up would be the average value because it took a steady incline. This also has a steady incline. So if I wanted the average value, I would just need to go like halfway up. But something like this that doesn't have any steadiness to it, what's the average value of that? No one knows. Like you can't easily common sense your way into that. So here's the solution to that. If you need to know an average value for something, it's going to be the area under the curve, like we did yesterday, divided by how long it is. And when you go to do the homework problems, the area might be able to be found from old geometry. Like if I were going to do the average value on this, I would do the area of a triangle from geometry time divided by how long was the triangle. You know that one. I can do area of a circle from geometry and cut it in half because it's only half of a circle, and then divide by how long it is. So geometry might be used. Or you might have to use our tricks from yesterday. If the graph looked like this, you'd have to use the trick from yesterday. You'd have to make rectangles, you'd have to guesstimate, we'd have to go like up through the middle, how tall is that? Up through the middle, how tall is that? Up through the middle, how tall is that? We would do our guesstimating game from yesterday if we can't use geometry. So there's an example 6. So example 6 has a picture in the margin. We're working from -3 to 3. We're doing a semicircle. So we don't need to do our math from yesterday to get the area figured out. We can just use geometry stuff. So for example 6, what's the formula for area of a whole circle?
X squared plus y squared equals r squared.
That's the formula for the like blue line itself, but formula for area of a circle is different. Like a 7th grade, like
Pi r squared.
pi r squared is correct. Okay, so we're looking to go this picture. We can use pi r squared with a radius of what on 277's picture? 277. We're off the page, yeah.
3.
3. So if we do pi r squared with 3, we'd get 9 pi if it was a full circle. But it's not a full circle. It's half of a circle. Yeah, so you could either go 4.5 pi or you could go 9 pi over 2, whatever you like. What's the length of the half circle from that picture? 6. So to do the average value, you have to do your 4.5 pi dividing 6 and go decimal if you like, or you could go the 9/2 pi divided by 6, like if you like fractions, you could do that. And you'd either get a 0.75 pi, or you get a 3/4 pi, or a 3 pi over 4, or like whatever makes you happy, you go with. Question about that concept? Okay. So the homework just kind of builds off of this. So let's look. 279 actually spills into 280. So 280, number 7 is like the example 3 that we did when I made this table. But they want you to just do 2 pieces, so it's easier. Then number 8 is a continuation of this same example, but they want you to do 8 pieces, so that's harder. Okay, but it's based off that same equation where y equaled x, same thing. 9 is a new question, unrelated. somewhat to anything we did. 9's the same as what we did here, same style, but it's a different equation. We're going to want to find midpoints, and then the equation is y equals x's divided by 3. So find some midpoints, make some radii, square them, add them, do the same process. The only difference on number 9 is that the equation is different. Number 9, with 6, a length of 6, they wanted 3 pieces. Then you redo it on number 10, and they want 6 pieces. So, good for them. Number 11 continues from the table I didn't write on the board. You had a table you wrote on your notes paper from the Rudy 16, that problem that we did together. Okay, so we had done 4 pieces. Number 11, they go easier for you to 2 pieces. And then number 12, they go harder on you up to 8 pieces. So you just do a rework of that problem 2 new ways, an easier way and a hard way. And we're only going to do the A's. I don't care about the questions with B's about the error percentages and stuff. I don't care about that. We're not doing that. So we're just doing anything with an A and a B. Just do the A. That's the straight math, the way that we did it, and then skip the percentage thing. 7 to 12 should be very much like what we did. Then we cut down to 21 to 26. 21 to 26 is like the math we just did a second ago with the average value in the semicircle. Okay, 21, 22, those are not geometry shapes. 21, 22, you're going to have to do the area doing mathy stuff from yesterday. 23 is a triangle, so that's geometry formula. 24 is a triangle, that's a geometry formula. 25, 26 are doable by geometry, but it's geometry plus cleverness, because what they have is like sort of some circular-ish kind of things, but then they've like done weird stuff to them. Like when they put the semicircle this way, we want the area under the curve. So like geometry can get you this, but you want that and that. So you can use geometry plus cleverness to figure out what's going on in those corners, but I'm not going to tell you how to do that. I'll make you clever tomorrow if you're not already clever overnight. But 23, 24 areas of the triangles are the areas underneath. That's just straight math. But 25, 26, you're going to have to be a little bit sly about how you use your circle knowledge to figure out some pieces that aren't actually in the circle but are like outside the circle. That's our thing, 7 to 12, 21 to 26, and then call it a day.